Bus is running late or you running late?
Me running late.
You running, okay. All right, so we're gonna go back to 7.4 today, which looks at a scenario that we've seen a number of times that now will give us a theorem to apply to that scenario. Okay, so here's what we call the side splitter theorem. And you've seen that picture before. That's the triangle with a triangle within a triangle. So you've got the two parallel lines here. Two things happen when you've got this side splitter. Number one, you have to have these two sides parallel. And number two, it splits the sides proportionally. So you'll see the way that I have it set up over there. Bottom over top equals bottom over top. You don't necessarily have to use the side splitter theorem. This is an optional theorem because we could go back to what we already did, which is comparing triangles to triangles. In other words, you could do BC over AC equals DC over EC. This is just a convenience thing. Top over bottom equals top over bottom. One of the problems with the side splitter is that people then want to use side splitter on the two parallel sides and it doesn't apply to the parallel sides. You have to go back to comparing triangles to triangles. Max, let me sit behind you. No, that's one empty seat, right?
Yeah.
Okay, thank you. Paul,
I'm not feeling a lecture.
what's up, fool?
Oh, we gotta stop at 2 trains.
Two trains.
Yeah, there's 2.
It's almost like two kids.
Two trains, not two chains.
I also got that for this chain.
The converse is just going, whoops, sorry, I thought I had a picture there, is going backwards. So, real quick, in case you're having trouble with converse, we've got the parallel lines, which gives us the side splitter, and then the other one, if you have the side splitter, then you have parallel lines. There's another one. Only 2 more. All right, so let's see it in action now. Find the length of x.
What was the proportion for it?
Top over bottom equals top over the triangle. Top over bottom equals top over bottom. There are a couple different ways to solve this. One, you could use a side splitter. The other one, you could go back to the traditional method that, not traditional, but the method that we did earlier, which is using triangle to triangle. Okay. So, first things first, how long is that? 37.5 minus x. Okay, good. So if we compare triangle to triangle, which is what we've already done, we would do 9 over 22.5 is equal to 37.5 minus x over 37.5. Right? Nothing new there. Cross multiply, solve that for that at value of x, please. Tell me what x equals.
Where'd you get 22? Added
9 plus 13.5. So
Oh,
I
it's
compared,
top over bottom.
yeah, I'm gonna do that in a second. This is not side splitter, this is
Oh.
just similar triangles. So I did top, or triangle over triangle.
Over.
Okay, so I'm not applying the side splitter theorem first time. Here I'm just using proportional triangles, or similar triangles, I should say. What's x? Michael? 22.5, can somebody confirm? Yes? Okay. Now, if we apply side splitter, solving the same problem, just a different way, we would do 9 over 13.5. So that's top over bottom equals top over bottom. Cross multiply and solve. Just to confirm that they both give us the same answer. We will in a second. Somebody's doing the calculation, right? I'm not just standing up here staring at you.
Yeah.
Okay. Thank you. Which we knew we would get. Either method works fine. Okay, now solving for y, however, y is not a side that's being split, so therefore you can't use side splitter, and you have to go back to the similar triangle method. 9 over 22.5 is equal to 7.5 over y. 22.5 times 7.5? 168.75?
Yeah.
So therefore y is equal to
18.75.
only way to solve for y. Josh, what's Mac?
I switched 9 and Y.
You switched 9 and y.
Yeah, position. Does that still work?
Yeah, because you're taking a length from the big triangle and comparing it to a length from the big triangle, setting that equal to the length from the small triangle, and yeah, works fine. Okay? Are we good with this? Excuse me, mid-segment theorem. We talked about a midline in a trapezoid. This is a little bit different, it just applies to a triangle. I think we actually talked about this. If we take any two midpoints in a triangle and connect them, we get something called a midsegment. That midsegment has two properties. Number one, it's parallel to the side that it intersects, and it's half the length. Oh, there's that. Looking good, Nick. Oops, let's go back to this. I thought I had a picture. We'll draw a picture in a second. So it's just like the side splitter theorem. The only difference is we make these midpoints. And it comes through there. It's parallel and it's half that length. So if this is x, this is x over 2. If this is z, how long is this? Z. If this is y, how long is this? Y, because they're midpoints. Okay. We're gonna skip this example because we need to move on, but here it is on a graphic. You could put it on a plane, measure the distances using the distance formula, and confirm that in fact all that stuff is true, that it's parallel and half the length. Okay. We're good? Yeah, good. There's Nick again. What's a corollary? Because I know we've talked about it before. Michael?
It's like a not that important, you know, I think that's what
Kinda.
Isn't it a theorem that isn't relevant enough to have its own theorem?
It's not big enough to have its own, it's like a sub-theorem. It's, again, it's not important enough to have its own theorem, but it's also based on another theorem. So this is, what we've done already. Instead of running just one segment through a triangle, we're gonna run a whole bunch, 3 or more parallel lines. And when you do that, it just slices the triangle into proportional parts, which looks something like that. So I took a triangle. First of all, I turned it on its side, just to make things interesting. And I ran a couple parallel lines through it. And so the theory, or the corollary I should say, says that if all these guys are parallel, then these sides are all proportional. So the nice thing about it is it allows us to set up proportions comparing any things that we want. So for instance, I could do x over 2.5 is equal to y over 2. What's wrong with that proportion? Jack?
there's
Two variables, therefore
so.
not solvable. We could do y over 2 is equal to z over 1.5. 1.5. Also not solvable. So we have to figure out a way that we can put this together. And you can put it together in any combination. And so this is the key to the problem. Setting up a combination between the two. So I'm going to do x over 2.5 is equal to this whole length, which is 8, over its proportional side, which would be this whole length, which is 6. Now that's solvable. Let's see, 6x is equal to 20. So excuse me. 26 10/3. Okay. And then once you have one of the variables, the rest of them all fall into place. I can put 10/3 in here and solve for y. I can put 10/3 in here and solve, or no, sorry. Once I get y over here, I can then take y and plug it in up here to solve. And you can keep going. Or go back to the original relationship. Y over 2 is equal to 8 over 6. That's a little bit easier. Z over 1.5 is equal to 8 over 6, and solve those. And hopefully if you've done it correctly, when everything is said and done, x plus y plus z would equal 8. Okay? So a couple things to be aware of. These have to be parallel in order for this to apply. Most of the time they will be, otherwise you're dead in the water. But you don't have to use this. You could go back to setting up similar triangles. Side splitter theorem, like I said, is just a convenience thing. It just makes things a little bit easier. Any questions on that? Beautiful. I think we're done. No, that's a giant rabbit.